Hello everyone, I am Narsimha SA, teaching at Government First Grade College, Koppa. In this video, we will learn about scalar fields and vector fields and related mathematics. Learning about electricity and magnetism requires learning also about some new mathematics. First prerequisite is partial derivative concepts. If a variable depends on many independent variables, then we need partial differentiation. Another primary prerequisite is there, that is zeroth prerequisite, and it is paper and pen. Without accompanied by paper and pen, just watching this video won't help you much. Now coming back to concept of partial derivatives, what it is telling, if you take a function which depends on now three independent variables x, y, z, then we will differentiate partially. These symbols are different from d by dx. They are called dou f by dou x. Dou f by dou x means differentiate f with respect to x, treating y and z as if they are constant. They are variable really, but while differentiating, you keep in mind that you have to differentiate with respect to x, means you treat x as the only variable and keep y and z as constant. Similarly, dou f by dou y means differentiate f with respect to y, treating x and z as if they are constant. An example may illuminate more clarity. If f of xyz is equal to x cube y plus 2z, then dou f by dou x is, if I treat y and z as constant, then this will give me 3 x square y, and here if it is like a constant, then 0. Therefore 3x square y. Similarly, dou f by dou y is equal to x cube plus nothing is there, second term also contributes 0. Therefore, dou f by dou y will become x cube. If you want to calculate dou f by dou z, then what it is? Yes, you are right, it is only 2. Now let us have a quiz. Here v of xy is given by, here only two independent variables, 3xy plus 9x. Then what is dou f by dou x? I will give you 7 seconds. Think. Okay, it's 3y plus 9. If you have told this, you are right. Another quiz. What is dou f by dou y here? I will give another 5 seconds. Okay, it's 3x. And after these prerequisites, let us know what we are going to learn in this video. We will learn about the concept of field, scalar field, vector field concept, then one kind of differentiation of the scalar field, that is gradient. We will define it in Cartesian coordinates. We will use symbolic notation, that is del operator. Then we will go to its geometrical meaning and physical significance. Mathematically, field is defined as, field is a region of space in which a physical quantity is associated at a very point of space. Okay, do not be confused Whenever we say region of space, it is not just the points, set of points in this region. At that point, everything, something physical that must be uh, defined. Something physical. Physical means where we or other objects can interact with that field. They can take back energy or give energy to that field or momentum. It is not just plain collection of the spatial points. You should distinguish. Then scalar field. Whenever you associate a scalar quantity in that region of space, not at one point, you should associate that scalar quantity at every point. Then we will call that as scalar field. Example, temperature distribution around a hot iron bar. This is the hot iron bar, and at every point now air will become hotter. Therefore, at every point we can keep a thermometer and we will know the temperature. Temperature is not only defined at this point, at every point, here also, here also, here also, here also. And uh, this is not very convenient, therefore I can go back to our friend Cartesian coordinates, y-axis, z-axis, x-axis. By doing so, every point, let me say point P, will have Cartesian coordinates x, y, z. Now, if I want to define temperature, associate temperature here, then that temperature is a function of coordinates x, y, z. It is defined in all the surrounding points of the hot iron bar. Similarly, I can define a vector field, a vector quantity smoothly assigned to each point of certain region of space is called vector field. In scalar field, what you associated at every point? A scalar quantity. In vector field, what you are going to associate? A vector quantity which has direction and magnitude. Not only a number is enough here. Example, magnetic field around a magnet or electric field around a charge. Till now, we have learnt the definition of scalar field and vector fields. Now, we will study how scalar field changes using a concept of gradient. It is something like how field, this is a problem now. We have to deal with the change of the fields from one point to other point. If you say it is P here and point Q here, and scalar field be pi. Pi at P, when we go to Q, how much it changes? Pi at Q. For this kind of problems, we can use the concept of gradient. Gradient in Cartesian coordinates, they are defined like this. You have to differentiate that field with respect to x coordinates, then multiply by I, unit vector I. Similarly, you differentiate f with respect to y, then multiply by unit vector j. Do that for z direction also, but multiply by k unit vector. Add all of them, you will get a vector quantity, and that is the gradient of field f. I think With problem, that definition becomes clear. Let us have this field f x y z is x square y z cube. What is the gradient of this f? Oh, first let us write like this with words only. Gradient of f is equal to dou f by dou x. That will become here x square, therefore 2x y z cube into I. Then partially differentiate with respect to y, therefore it will become x square z cube into j cap plus partially differentiate with the z, then you will have x square y multiplied by 3z square into k cap. Let us have one more example. For example, a scalar field be pi. Now pi is equal to x, y, z. Therefore, gradient of pi, grad pi will be dou f by dou x will give you yz into I. Then partially differentiating with respect to x, I will have xz j cap plus similarly I will have xy here k cap. If we define another operator like this and denoted by this symbol called del, that is called del operator, it will be very convenient for future purposes. Therefore, what it is telling, this is an operator without writing what to be operated on, it is incomplete, but this operator tells that I should do partially differentiate with respect to x, then multiply by I cap. Partially differentiate with respect to y, multiply by j cap. Partially differentiate with respect to z, multiply by k cap, then add all those things, that is the del operator. Using this notation, I can write this grad f as del f. Grad f as del f. Further, we will, whenever I say gradient, I will write like this. Now, I want to give a geometrical meaning. That means, for that, if you say point P and here it is the gradient, if you say, what is the meaning for that vector? How to relate it to the variation of the field, change in the field when I move by a small distance q. Let us analyze like this. Instead of going directly from A to B along dr direction, I can move from A to some other point only along x direction. Then I will have some change in the field. df is equal to dou f by dou x into dx plus, if I move only along y direction, dy, that will be, then the variation will be dou f by dou y into dy. Then how much will change in the field? If we move along only along z direction, then that will be dou f by dou z into dz. Now I want this variation to be written as a scalar product of two vectors. How to do it? I can do it by like this. Do f by dou x multiply by I plus dou f by dou y multiply by j dou f by dou z into k. This is the one vector dotted with dxi plus dyj plus dzk. Okay, I will give 3 seconds. You can verify it. It is the dot product here of two vectors. Verify. Okay, if you after taking dot product, if you get this one, then this is equal to df. Therefore, df is like this. Then df, now what is this vector? That is gradient of the field. Dotted with what is this vector? This is nothing but dx vector, dy vector, dz vector by vector addition rule. That is nothing but the dr vector. Therefore, this is nothing but dr vector. In beautiful computer handwriting, that will become dr vector is like this. Then df we consider that will be like this, and this can be written as dot product of gradient of field and that small infinitesimal displacement dr. This can be written using the definition of dot product gradient modulus of gradient of field. This is not determinant, this is now modulus. Anyway, this is a vector, it will have magnitude. This is the magnitude of that vector, gradient vector, into dr, magnitude of this vector, into cos theta. Now carefully observe, when I move along the gradient direction only, that is the direction of f. If I move along that one from point P to some point Q, then what is this angle theta? That is the angle between that infinitesimal displacement vector and the gradient. And now it is along the direction, therefore theta will become 0. Therefore, grad f into dr, in that case when I move along, is the dr, and cos theta is maximum. Therefore, when I move along the direction of gradient, I will have maximum change in the field. Therefore, rate of change will be maximum when I move along the gradient direction. That maximum rate of change will give you magnitude of the field. Therefore, now I have a geometrical meaning independent of coordinates, that is magnitude of the gradient field gives the maximum rate of change at that point. If I move along any other direction, then the rate of change will be minimum. If I move constant distance from this point in this any other direction, I will have minimum. If I move along the gradient direction only, I will have maximum change in the field. I have taken this definition from Wikipedia. The gradient vector can be interpreted as the direction and rate of fastest increase. In clear words, if the gradient of a function is non-zero at a point P, the direction of the gradient is the direction in which the function increases most quickly from P, and the magnitude of the gradient is the rate of increase in that direction. As I have already told, if you move along any other direction, you will have lesser change in the field. If you move along the gradient direction only, you will have maximum change in the field. Maximum change in the field. Okay. And